Alright guys, today we're going to learn about Hess's law. It's been a while, so let's talk about why we would use Hess's law. We use Hess's law to find delta H. Guys, what is delta H measuring? What is that? Heat, either released or absorbed in a chemical reaction, right? That's what this whole chapter is about, thermochemistry. Whether or not a reaction absorbs or releases heat, and we can actually measure it, so we're going to quantify it. Hess's law is just one of the ways you can do that. So, what I would like to see you guys have out is your Chapter 4 guided notes. You've got to fill in some of the words that go on these slides. So please have that out. And that's about it today. Okay, so here we go. Hess's law, here's the definition. It states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all the changes. That definition kind of, it'll make more sense once we go through these problems, but let me see if I can help you understand what that definition is saying. It says regardless of the multiple steps of a reaction, the total enthalpy change for the reaction is the sum of all of them. So here's just an example. If this is where my reactant started, okay, and we're measuring enthalpy on this y-axis. So if my reactants have that much energy, and let's say this reaction didn't happen in one step. Let's say it kind of happened in, I don't know, 3 or 4 steps here. Okay, we finished down here at the products. So there's 1, 2, 3, maybe 4 steps to this reaction. Well, what Hess's law says is it doesn't matter how many steps. It's something we don't really consider. When we're trying to figure out the total enthalpy change for the whole process, delta H is measured from where you end up, so the products here, compared to where you started. That's how you calculate delta H, final minus initial. So that's what Hess's law is saying. It doesn't matter how many steps, how many stages of the reaction. Okay, well, we can add equations to come up with the desired final product. We can add up equations. We're going to be doing this all day. We're adding equations to come up with the desired final product, and then we can add the delta H values for those reactions as well to come up with the final delta H value. So Hess's law, I like to think of it as a game. Okay? The game has 2 rules. 2 rules for Hess's law. Number 1, if the reaction is reversed, the sign of delta H is also reversed or changed. So if the reaction is reversed, the sign of delta H is changed. That's rule number 1. Rule number 2, if the reaction is multiplied by some number, you're going to multiply delta H by that same number. So if you multiply the reaction, you also multiply the delta H value for that reaction. Okay, so 2 rules. What I've got now, guys, is one example problem that's not in your notes. So you're going to have to watch up here as I do the example problem. And then to finish up, we've got 2 example problems that will go through how to do Hess's law. Sound good? Okay, let's get started. Here's the example problem. I'm going to spend some time on it. And it's not in your notes, so you need to look up here so that you can understand it. It says you want to know delta H for this reaction. Okay? This is the reaction I want to know delta H for. The reaction that we want to calculate delta H for, I call the target. This is my target reaction. In the end, when we add up all of our different reactions, this is what we want in the end. Okay? Maybe we can't calculate delta H for this reaction. Maybe I don't know, because of certain situations, we can't calculate delta H. But let's say we did know, these are our givens, equation number 1 and equation number 2, And we did know the delta H values for those equations. So what Hess's law does is we can use these two equations right here, manipulate them and change them in such a way as when we add them together in the end, it's going to cancel out everything except for our target equation. So we're going to add those two reactions together to get our target in the end. That's why I call it the target. Okay, so let's go through how you would do this, okay? What I always like to do is look at the target equation and maybe find something here, like the nitrogen. Do you see nitrogen in one of our two given equations down here? Where at? Number 1 has nitrogen. And also, is it on the left side? Because we want our nitrogen in the target to be on the left side. Is it? And it is. Okay? Now, let's look at the number of moles. How many moles of nitrogen do we want in our target? 1. How many do we have in our given? 1. So it looks like to me, if I was doing this problem, that I would want to keep number 1 as it is. Okay, so what I like to do is make little notes on the given equations on what we've got to do to it. We want this one to stay the same, so I'm going to put keep. That means for the delta H, I'm going to keep it the same as it is. We're not going to change it at all. Okay, let's go to something else. Equation number 2, if you look at it, is there something in equation number 2 that is in our target equation? What about this 2 nitrogen dioxides? Is that in our target? Yeah, and it's the same mole ratio too. We got 2 nitrogen dioxides in the target. So what do you think we should do with equation number 2? We're going to keep it. Okay? But if you look at our given equations, is there something in these given equations that doesn't show up in our target? What is it? What about this 2 nitrogen monoxides? And this 2 nitrogen monoxides? They're not, nitrogen monoxide is not seen up here in our target equation. So what do we need to do? What do we need to make sure happens? That they cancel out, okay? Will the nitrogen monoxides, if I add these two together, will they cancel out? Yeah, because I got 2 on the left here and 2 on the right will cancel out. Okay? Now, what about my 2 oxygens? If I add these together, won't that be 2 oxygens? Okay, and so that's kind of what the game you're going to be playing is to make sure that everything cancels out in your givens so that your target equation is what you're left with in the end. So when we add these 2 reactions together, let's add them together now. I've got N2, so I'm just going to keep everything on the left on the left. I've got, what's 1 oxygen plus 1 oxygen? That's 2 O2s plus, I've got 2 nitrogen monoxides. That's everything on the left. Now let's list everything on the right. Now be careful. Nitrogen dioxide is different. We can't add these together because they're different substances. So I'm going to put 2 nitrogen monoxides plus 2 nitrogen dioxides. Now let's cancel out like terms. The nitrogen monoxides will cancel out. If they're the same on both sides, you get to cancel them out. And so what I'm left with is N2 plus 2 O2s goes to 2 nitrogen dioxides. Okay, so what we did is we just added our given equations up so that it makes, is this my target? Yeah, when you can add them together and you make the target, you've done the problem correctly. But is that my answer? No, it wants us to know and calculate delta H. Well, if we kept equation number 1 as is and kept equation number 2 as is, all we have to do, because we added them together, is add these 2 values together. So what's 180 plus a negative 112? Is it 68? So positive 68 kilojoules. So that's really the answer to this question. So again, what we're doing is if you can't do this reaction and calculate its delta H value, another way you can figure it out is by using other equations and using Hess's law to manipulate them so that you can make the target equation and calculate your delta H value. Sound easy? Can we do it? Okay, I've got 2 practice problems for you to try. So here we go. So we did get it right. 68 kilojoules was our answer there. So good job. Okay, practice problem number 19. Let's go through this one together. It says to find the delta H for this reaction. So what we've got is carbon in the graphite form being converted to carbon in the diamond form. So diamond, graphite, coal, it's all made of carbon. But it's how the carbon atoms are arranged that determines whether it's graphite, diamond, or coal. Okay, so you can take graphite and change it into a diamond. Let's figure out the delta H for this process. Okay, here's the given equations for us. It gives us 2 of them. So what I would like you to do in your book is kind of maybe make a box around this and put target. Okay, this is our target equation. When we're done adding these 2 givens up, these 2 given equations, when we're done adding them up, it should equal our target. Okay, so you guys help me out with this one. What I like to do is look at the target first. We need carbon in the graphite form on the left. Which one has carbon in the graphite form? Number 1. Is it already on the left? It is. 1 mole up in the target, 1 mole here. So I think, what should we do with equation number 1? Let's keep it. Make a little note of that. We're going to keep it as is. We're not going to modify it at all. Okay, now let's go back to our target. It looks like we need diamond, carbon in the diamond form on the product side. Which one of our given equations has carbon in the diamond form? Number 2. But diamond's on the left side. So what do I need to do here? We need to reverse. We need to reverse equation number 2. Okay, so I'm going to rewrite it now. I'm going to rewrite it and let's reverse it. So now we've got CO2 with an arrow, and that goes to carbon in the diamond plus O2. Now, if I reverse equation number 2, very important, what do I need to do to the sign of this delta H? Reverse it. So it becomes positive 396 kilojoules. Okay, so now that I've rewrote it, I'm going to scribble this one out. I don't want it to confuse us anymore. Okay. So I think maybe if we added them together now, let's see, would it make my target equation? If you see in the target, there's no CO2 and there's no oxygen. So we've got to make sure that they cancel out. Will they? Let's see. So let's add these 2 equations together. So we've got carbon in the graphite form plus oxygen plus, now we've got CO2 on the left, so I'm going to put CO2 here. Okay, let's find out let's list everything that's on the right side or the product side here. We've got CO2 right here. What else is on the right? Well, we got carbon in the diamond form plus this oxygen. Okay. Now, can we cancel out anything? Yeah. I've got oxygen right here on the left, can cancel out with this oxygen on the right. My carbon dioxide on the left cancels out with this carbon dioxide on the right. So in the end, when we added them together, we get carbon in the graphite form goes to carbon in the diamond form. Did we make our target? Yes, we did. So now we just got to add our delta H values together. So we've got delta H of minus 394 kilojoules. And we added that to this delta H of positive 396 kilojoules. What does that equal, guys? 2 what? 2 kilojoules. So my delta H is equal to 2 kilojoules. All right, so does that make sense? Would graphite, guys, have to absorb energy or release energy in order to make diamond? It would have to absorb energy, right? It would have to absorb that heat energy in 2 kilojoules. Now, there's a lot more that goes into it than just heat. If you wanted to take some graphite and make diamonds, there's more that goes into it than just heat. There's pressure, and it takes a long time as well. So it's not just as easy as adding 2 kilojoules of heat energy.
Can we do that for lab?
We should. We should make diamonds, huh? Okay. Practice problem number 20. Here we go. I want you to find the delta H of this reaction. So this is my target. So on your books, I want you to put target equation. That's the one I want in the end. This one's a little more complicated because it gives us, I think, 4 givens. So your job is to manipulate these given equations so that when you add them together, you make the target, keep track of what you're doing to delta H here, and let's calculate delta H for this reaction. That's what I want you to do. Okay, I want to give you some time to try this. But one thing I wanted to tell you before I give you time is I don't really like fractions, and maybe you guys don't really like fractions. What is 3/2 in a decimal form? 1.5. So if I were you, what I always do when I see fractions is I change it. Okay. So instead of 1/2, I put what? 0.5. Okay. So if you see fractions in any of them, I like to change them to a decimal form. Anyway, try to manipulate these 4 givens. Use Hess's law. Calculate delta H. Let me give you some time to do that. So if you're watching the video, please hit pause until you have an answer, then hit play. Okay, let's see how you guys did. Hopefully you gave it an honest effort. I know this one is quite a bit more complicated than the previous examples. But I promise you, if you gave it an honest effort, you're going to learn something as we go through this explanation of it. So here's how I would approach a problem like this. Of course, you've got to look at the target equation first. Okay? What I do is just pick something out in the target. So, for example, this boron. We've got 2 moles of boron. Where do you see boron in any of these givens? Is it only in number 1? Yeah, it's only in number 1. And look, I already have 2 moles on the left of boron. So what should we do with equation number 1? Keep it. Okay, so let's write that note. Let's put keep. So that means the delta H, everything here, even the delta H is going to stay the same. Okay? Now let's just keep playing that game all the way down. Where do you see H2 at? Because I've got 3 moles of H2 in the target equation. Where do you see H2? In the third equation. Is that the only place you see H2? It is. So, guys, the only way to get 3 moles on the left, it's already on the left, but I only have 1 mole. What do I need to do with equation number 3 then? I need to times this by 3. So here's the note that I make. Times by 3. Okay, so I make a little note of times by 3 this equation, which means that I've got to do what to the delta H here? I got to times this by 3. So make a little note by the delta H, what you're doing. Okay? Okay, so let's just continue on and look at the target equation. Now, the only other thing in my target equation is this B2H6. It's on the right. And how many moles do I have? Just 1. So I need that to be on the right with just 1 mole. Where do you see B2H6 in your given equations? Number 2. But it's on the left side here, right? So what do we got to do to this equation? Reverse. So I'm going to put reverse But if I reverse the equation, what do I got to do to the sign of delta H? So I'm going to put reverse by the delta H as well. Because in the end, we need to make sure we kept track of what we're doing at delta H. That's really the most important part. Okay, now, why did they even put equation number 4 in here if there's no water in the target equation? Because there's water in the other ones that we've got to cancel out, correct? So, let's look at the phases here, guys, is going to be important. What does this little L mean? It's a liquid. What does the G mean? It's in the gas phase. That is going to be important when we look at these equations to try to get it to cancel out. Now, of course, there's no water in the target, so we need to get rid of all of them. Where do you see water in our given equations?
3.
Number 3. Okay, we've got 3 moles of water here in the gas phase, but we reversed it, right? So in the end, this is going to be over here on the left side, but I've got 3 moles of it. What do I have to do to equation number 4 then? I need to times that by 3. So I'm going to make a little note to times it by 3.
Hey, I got a question. Number 3, on the third one, you times that by 3, you have 3 H2O, and it's on this side.
Okay, yeah, we times equation number 3 by 3 and got, so that would give us 3 H2O liquids on the right, correct? And that will cancel out with my 3 H2O liquids on the left of this one. Yeah, good call. Hey, if we added these together now, do you think we could form our target?
Yeah.
Let's find out, okay? So what I'm going to do, I don't have a lot of room. You have more room on your paper than I do. But I'm going to rewrite them following these rules that we said we were going to do. So we're going to keep number 1. So I'm just going to write it down here. So 2 borons plus 1.5 O2 goes to B2O3. And let's also track what we're doing to delta H. Does it stay the same, guys?
Yeah.
It does. So a minus 1273 kilojoules.
Wait, why doesn't the oxygen cancel out?
Well, it will. I haven't canceled anything out yet. I'm just rewriting them following what we said we were going to do here. And then we will cancel out. Good point. Okay, let's write the second one. But what did we say we were doing to number 2? Reversing it. So now my products become my reactants. So I'm going to rewrite it. So B2O3. So this right here is now a reactant. Plus 3 waters. But I'm going to keep track of the phase that the water's in. That's the gas phase there. Okay, and that goes to... Now this becomes a product. So B2H6 plus the 3 oxygens here. Okay, now if I reversed it, guys, if I reverse the equation, what do I got to remember to do to delta H? Change the sign. So now it's not negative, but it's positive 2,035 kilojoules. Okay. All right, so we're doing good so far. What did we say we were going to do to equation number 3? Times it by 3. So I'm going to go ahead and just put and times it by 3. What's 0.5 times 3?
1.5.
It's going to be 1.5. And then how many moles of water will we have here? 3. Okay, so let's rewrite that down here. So 3H2 plus 1.5 O2s. And that goes to 3H2O. I'm going to put the liquid phase here. Okay, now if we times this equation by 3, what do we got to remember to do with our delta H value? Times it by 3. So when we record our delta H down here, let's do negative 286 times 3. You should get negative 858 kilojoules. Did you guys get that? Okay. Now we just got 1 left. What did I say I was going to do to equation 4? Times it by 3. So I'm just going to go ahead and distribute the 3 through. Okay, so we've got 3 H2O in the liquid phase goes to 3H2O in the gas phase. Now, if I times the equation by 3, what do I got to remember to do to delta H? Times it by 3. What's 44 times 3? 132. Okay? So delta H is equal to 132 kilojoules. Correct? Okay, now let's see if we add them together. I don't have a lot of room, but I think I can show you if we add them together. Now, before we add them together, let's cancel out like terms. If you look up here at my target, is there any oxygen? No. So hopefully my oxygens will cancel out. I see 1.5 moles of oxygen here, 3 moles of oxygen here, and 1.5 moles of oxygen here. Now, if they're on the same side, we can add them together. What is 1.5 plus 1.5? That's 3. Won't that cancel out with the 3 oxygens right here, guys? It will. Okay, so they're gone. Let's go to this. Let's go to this B2O3. Does that show up in my target? No, so that should cancel out. If there's B2O3 on the right, let's look for something on the left. Is there one? Yeah, if you look right here, B2O3 and this one, 1 mole and 1 mole cancel out. Okay, let's just keep going down the list. Water does not show up in my target, so we've got to cancel out this 3 moles of water in the gas phase. Does that cancel out with anything else? Yeah, in equation number 4, 3 moles in the gas phase on the right side. So that cancels out. Okay, now does B2H6 show up in my target? And the answer is yes. It's the only product that we have, so we're going to keep that one, hopefully. It doesn't cancel out. What about the H2? Is there H2s here? Yeah, there's 3 of them. So does it cancel out with anything over here? Hopefully not, and it doesn't. Okay. What about this 3H2O liquid? Does that cancel out with anything? The answer is yes. On the 4th one, it's 3H2O liquids on the left. Okay, now I'm done canceling everything out. Let's see if what's left. 2B. 2B, that's okay. What else is on the left? The 3H2. 3H2, that's good. That's everything on the left, right? Now on the right, what's left on the right? It's just the B2H6. So we did everything correctly. We did form our target equation. Now, is that our answer? No, what we wanted to know was what the delta H value was. So now that we've kept track of it and we changed it as we went, let's just add these together and see if we can get the right delta H value. So negative 1273 plus 2035 plus a negative 858 plus 132. What did you guys get for delta H? Positive 36 what? Kilojoules. Okay, so the answer again was positive 36 kilojoules for this reaction. Okay. Okay, how many of you guys did get that right? Okay, and if you didn't, can you see where you went wrong? Okay, I think we can do these problems. They're actually, I think Hess's law problems are kind of fun. You get to cancel some equations out, manipulate them so that you form the target. What's funner than that, guys? Seriously. Literally everything? I don't agree. I think Hess's law is pretty fun. Hey, before we quit, hopefully we learn how to do some Hess's law type problems, but to give you some more practice, I've got Hess's law worksheet in your student workbook. So please turn there now. Hess's law worksheet is what it's called. Let's see if we can get some of these right in the student workbook, and hopefully that helped.